Hello everyone, I'm Gong Kaijie from Zhejiang University in China. My advisors are Professor Dongwei and Gaoyi. We are here to present our work, Programming Embedded IoT Application in Natural Language with IoTPilot. Embedded OS such as IoT and therefore play an important role in IoT application development. These OS typically provide different abstraction layers for reading and writing. Developing embedded IoT applications on this OS remain highly challenging because developers must understand different programming models, different I/O operations, and different system calls. In recent years, large language models have introduced a new paradigm for application development from natural language to code. Existing work has achieved better results on code generation datasets like MBPP, thanks not only to the better capability of LLM, but also to the introduction of mechanisms such as self-debugging, retrieval, argument generations, and multi-agent systems. These methods further enhance the ability of LLMs in code generations. We then evaluated the performance of existing technicals on the task of generating embedded IoT applications. We construct a test set consisting of 15 IoT-based IoT applications. The results show that both native LLMs and Copilot perform poorly. Moreover, when we increase the complexity of IoT tasks, such as programming from initial blink to subset ambiguity or cope, the performance of the existing methods significantly declined. So we use IoT-based ambiguity application as an example. We record the code versions generated by the LLM during the self-debugging process. We have the following observations. The code version in Figure A uses incorrect headers and APIs. The code version in Figure B uses correct headers but incorrect APIs. These APIs are correct for the Linux version but not so for the current IoT OS version. The code version in Figure C uses correct APIs but incorrect headers. This results indicates that LLMs may lack a context understanding of the relationship between embedded OS specific headers and APIs, likely due to the insufficient training data in this domain. Such discrepancy led to inconsistency between the LLM internal and external knowledge. Internal knowledge such as Linux version APIs and external knowledge means the local OS version APIs. This issue results the poorly code generated quality. To address the conflict between the LLM internal and external OS knowledge and the directory solution is post-training the LLM with technical like direct preference or optimizations for preference alignment to coordinate internal and external knowledge. However, due to the lack of datasets related to embedded OS, it is difficult to construct high-quality children and reject the training pairs. Therefore, instead of fine-tune the LLMs, we introduce an online preference alignment methods during the inference stage to align internal and external knowledge. This approach allows for dynamic adjust the LLM outputs without changing model parameters, making it more aligned with the specific OS. This strategy significantly improves the quality of code generations for specific embedded OS. Specifically, we introduce a context-aware auto-calibrating chain to align LLM internal OS knowledge with external embedded OS knowledge, increasing the success rate of headers usage. Additionally, we introduce an SFG-based code pattern reuse change to align LLM internal OS knowledge with widely used Linux code knowledge, enhance the accuracy of generative API call relationships. Firstly, we introduce the context-aware auto-calibrating chain to align LLM internal OS knowledge with external embedded OS knowledge. The foundation in workflow of IoTPilot is mainly two existing methods. First, we collect code wrapper and API documentations from embedded OS and establish a vector database. Then, for a user query such as implement an MQTT connection function, the LLM process the query and generate the corresponding code and executes it. Next, it collects compilation and runtime information of the generated code and uses this information in the next iterations to produce the revised code. In IoTPilot workflow, apart from the step mentioned above, one co-design is the introduction of a context-aware chain-based association miner before the LLM outputs. This chain establishes an online context of OS-specific API headers to align API headers preference online. This context includes various types of relationships between API and the headers. First, complex relationships. For example, MQTT connect is suitable for Linux, where IoT use different APIs. So MQTT client connection is complicated with other APIs. Then strong association relationship. For example, MQTT client .h and PAHO MQTT.h must be included together. So these headers are strong associated. Third, weak association relationship. These are relative less dependencies. Realize LLM's outputs to strongly associated context items to ensure code correctness. We avoid alignment with complicated associated context items. Strong association are akin to chosen data in DPO, whereas complicated association resemble reject the data. These approaches effectively improve the accuracy of generative API headers. The key to the context-aware auto-calibrating chain based on association miner is how to quantitatively align the relationship between different APIs headers from LLM internal knowledge and external regular documents during the self-debugging process. We propose a specific LLM-based distance measurements math. First, for a set of API and headers, we first use LLM to extend these descriptions by prompting the LLM to describe the function of the current API and highlight aspects relevant to the problem's descriptions. This is additional related information to each API and the headers enrich its semantic content. Next, we extract embedded representations from these extended descriptions. These embeddings capture the semantic features of the APIs and the headers. Finally, we use cosine similarity to calculate the distance between APIs and headers. Then even when using the correct APIs and headers, the generated API call sequence often contain errors. To address this issue, we leverage a broad code base, including Linux code to guide the generation of API call sequence. For this purpose, we introduce a state transition-based code reuse chain to align the LLM internal OS knowledge with external Linux code knowledge. The key to the code pattern reuse strategy involves introduce the state flow graph defined as SFG object. The state are vertices in the graph representing the program's achieved state, such as network initially state, typically indicated by the return value of network connection APIs. The address of the graph are specific APIs that cause this state transition. This method is used to instruct API and they are introduced program state changes from Linux code. Then in the online phase, we constrain the LLM's output to align with the instructed SFGs, enhance the generated programs adhere to correct program state transformations. This project ensures that the generated code logically follows the expected state transition flow. Specifically, the workflow for the code pattern reuse chain based on SFG in the online phase. First, instruct the SFG from each round of self-debug outputs and search for the top case memory SFGs in the offline datasets. Then use LLM for pattern matchings and generality analysis report, which include the potentially miss API and the return value validation logical. Next, convert the instructed logical into JSON format to create online context. Finally, use the online context as input for the next round of self-debugging, ensure the LLM meets logical constraints in the next code generation code. Finally, to enhance the IoTPilot capability for generating complex IoT program, we introduce a multi-agent code generation framework based on Unite debugging for a user problem. IoT first decompose the complex task into multiple sub-programs, then perform self-debugging on each sub-program individuals, and finally integrates the code generated for each sub-programs. The generated sub-programs and the integration of complete code both utilize our online preference alignment to improve the quality of code generation. We have released the IoTPilot to the VS Code plugin market. The usage is mainly to existing tools. We have developed IoT Evo and evaluation datasets for embedded OS-based IoT code generation include applications based on IoT, therefore Kaijie, NG, and FreeRTOS. The baseline include direct math, auto COT, and map code. Direct math prompt LLMs to generate code by leveraging their built-in capabilities. Auto COT implies COT math to decompose problems into step-by-step solutions. Map code imply RAG and self-debug at the same time. Our evaluation metric include completion pass rate and generation accuracy for the API and the headers. On the IoT platform exists math when using GPT or DeepSeek coder. We found that IoTPilot shows significant performance improvement in applications. The RAG functions have different implementation across multi-operating systems, especially the MQTT-based applications. This is because our online preference alignment resolve conflicts between MQTT APIs from different OS versions. We also evaluate IoTPilot accuracy in generative APIs and headers, and the results show that IoTPilot achieves higher accuracy compared to the baselines. We conduct an ablation study of two preference alignment reasoning chains and found that both chains significantly improve the performance of the generation task. We also evaluate IoTPilot performance on different embedded OS. The results show that IoTPilot can achieve better performance on different embedded OS. We observe that different operating systems versions might use different headers and APIs, which can lead to conflicts, such as therefore .h was deprecated in the new version, reducing the performance of existing methods. IoTPilot can resolve this conflict by exploiting API header relationships across OS versions through dynamic context constraints. We also compare the IoTPilot with existing code generation tools and observe that IoTPilot outperforms existing tools. This is mainly due to the following reasons. Existing tools often incorrectly reference libraries such as NanoCope, UDP, and COPE. The frequently miss critical headers like MQTT.h due to the missed context knowledge. Additionally, these tools tend to confuse the use of different MMA version libraries as well as the ILQ and ILQ-ARC libraries. IoTPilot in fact will address these issues through online preference to find the correct libraries. Finally, let's showcase our IoTPilot plugin. Initially, user can configure parameters include selecting different LLMs and contexts means enable online preference alignment. Then, similar to existing tools, user can engage in multi-turn dialogues with IoTPilot to refine the generated code. So this is my presentation for IoTPilot. Thank you for your attention.
Hold on. Can you hear us online?
Yeah, hello.
Okay, go ahead.
Okay, very interesting work. And this is Le Ming from Hong Kong PolyU. And I have a question I'm curious that what kind of programming tasks are you focusing on? Because I noticed that you use pass at k as an evaluation metric. So this means that the programming task should have confirmed results. So what if the programming task is like, for example, developing a human activity recognition system that will output recognition accuracy, but that is not the only correct answer because we need to iteratively improve the program to achieve better performance. So I'm curious that can your system support those kind of tasks?
Were you able to hear the question?
No, I'm sorry, I didn't hear it very clearly.
Okay, well, maybe you could send him an email offline
Okay.
to ask the question.
Okay.
Yeah, thank you again. Let's thank him one more time.
Thank you.